Last class, we looked at certain problems where we talked of forces on a single body, and we saw how to apply Newton's law to problems like that, where we first drew a free body diagram and then used Newton's second law on that problem. Now, you could also encounter problems where there could be more than one bodies involved. Example of this could be there is a mass m1 tied to a string to another mass m2, and this is being pulled with a force F, maybe through a string or through just being pulled with a directly to a force F is being applied to m2. So, here we have a case where there is more than one body is involved. So, here generally the way when we solve these problems, we may have to draw the free body diagram of each body separately, and then we apply, after we draw the free body diagram, then we apply Newton's second law to each body. But what we will have to realize is when we do that, whatever is the interconnection between these two bodies, we have to make sure that we use Newton's third law, that is action and reaction of on the connecting body is there, and so that will give us a common link between these two bodies. So, a common link will come from Newton's third law, and also what we will need is that if we look at kinematics, then if these bodies are moving, then accelerations of bodies 1 and 2 will be related, and this relation will give us another equation to solve the equations. For example, let us say if these bodies m1 and m2 which I talked of, they are lying on a table and they are being pulled in the horizontal direction. If the string, and this is a string which is there or a cord between these two bodies, if now this cannot extend, its length is constant, then we can clearly say the acceleration of body 1 is equal to the acceleration of body 2, because the length of the string does not change. So, these sort of relations between accelerations is what you will have to look for in problems. In simple problems like this one, the accelerations of m1 and m2 are equal, but there may be more complex problems where acceleration of body 1 and body 2 will not be equal, but there will be some relation, and we will also look at some of these problems, not today, maybe in 1 or 2 classes from now. So, two things to keep in mind when you have multiple bodies. One is kinematics, and the second thing we keep in mind, let us write that down, is the relation between forces between the two bodies or the connecting element between these two bodies, and for that we have to realize that we have to use Newton's third law, that if FAB is equal to minus FPA. So, using these we can work out the problems. So, now let us have a look at the general procedure which we have developed for solving these problems in mechanics, and I am now going to do an analysis of the procedure which we have developed. So, our procedure is that procedure for solving problems so you have a body or a particle on which forces are acting and due to which the body accelerates. And we have to work out one of these things. So, now when we talk of forces, as we said, forces on the particle, we have the weight which is due to gravity. We have already seen this. Then we will have some contact forces, and these contact forces we divided in two parts, a normal reaction and friction if this is a solid in contact with another solid, and we could have other contact forces like a string or a spring which is connected to a body, connected to particle. So, as we have seen, for example, let us see, we had this block on a table which is block has a mass m and there is a string which is pulling this with a tension T. So, if I draw the free body diagram, let us say this angle is theta. So, if I draw the free body diagram of the block, I will get its weight acting down, there is a normal reaction, there is a friction force. So, these two N and F are the contact forces, and we have the tension T, and because of which the body accelerates, and due to the constraint of the problem that the body moves on a plane, acceleration will be equal to acceleration as a scalar only in the x direction. So, on one side we draw the free body diagram, on the other side we have kinematics. So, when you solve a problem, you draw the free body diagram and you write the kinematics equation, and then all what you have to do is sum of forces is equal to m times a. Equate the left hand side and the right hand side. In the left hand side only the free body diagram comes. We do not bother about the kinematics when we draw the free body diagram. All we have to be careful about is that we are drawing the free body diagram with all the forces shown properly. And the other thing we have to be careful about is that we should always show the direction of our coordinate axis. So, we show x and y, and as we have seen, maybe another student will solve the same problem by choosing this. I am now using star, he uses x along this string, y perpendicular to the string, so that can also be done. So, for these what we will have to do is resolve, depending on what my x and y are, either resolve the forces or resolve the acceleration along the appropriate directions. Now, what will happen is if we try to look at a physical problem, the physical problem which I have told you is, okay, this is a block, this is being pulled by a force, and because of which it is lying on this table and it moves with an acceleration. Now, physically when you look at this problem, the mass of the block is something we will be able to know, and that will be given to you in most problems. The force T which is being applied, either this will be known or this will be an unknown force, unknown quantity. And similarly, the acceleration would either be given to you or this would be an unknown. Of course, if the problem has to be solvable, both of these cannot be unknown, only one of them will be the unknown. Now, what we realize is when we draw the free body diagram, then because of the contact force, so this is what we have when we draw the free body diagram. Then we have a normal reaction, we have a friction, we have the weight which is acting, this force because of the external body, the string, the tension like this, and acceleration. So, now our number of equations from Newton's law is 2, one in x direction, one in the y direction. Okay? And so now if we look at this, normally N and F, the normal reaction and the friction force, physically would not be defined. We will not be able to know them a priori. In a given data, how do you know if I tell you this pen is there, this is lying on the table? Then by the definition of the problem, I will be able to measure the mass of this pen. So I can say what is the weight of the pen. But how much force is the table exerting on the pen will most likely not be known unless if in a contrived problem I give it to you. So if we look at this, then what we find is N and F, these are two unknowns. In addition to that, what we have shown, either T or A, one of these will also be an unknown. So now we have three things we have to find: N, F, A or N, F, T. If acceleration is known, now acceleration may be given to you in terms of the block starts and stops in this way, so you use kinematics to find acceleration. So that could be one way, or it could be given to you directly. But now we have only two equations and three unknowns. So how do we get the third unknown from? And that comes from the fact that this situation, when the body is under this, either the block could be at rest or it could be moving. If the block is at rest, then we have the third information that acceleration is equal to 0. So then we have two unknowns, N and F, and we can solve the problem. But if the block is moving, then let us say the tension is given, so acceleration is not known. So then, but there what we have is, then F in this case is related to N by F is equal to mu k N. And so therefore this gives us that extra relation. In case if the block is just about to slip, for impending slip, we will get F is equal to mu s n. So depending on what type of motion, so then friction is related to normal reaction, and then we work out the problems. So this is what we have to keep in mind. Now maybe there may be a problem where you do not know if the body is moving or not, and we have discussed a very special simple case of this. So in such a case, how do we do? So applied forces are given. All the forces which are applied forces, maybe I will specify, on the body or on the particle are given to you, and you do not know what type of motion takes place, whether the body moves or not, or if it moves then with what acceleration. And in these problems, particularly if friction is involved, then and if here you have to find the value of friction at the contact surface. So what we do is, first we will assume that there is no motion. We assume the system is at rest, and then that means acceleration is equal to 0. So when we do that, now we can from our free body diagram and kinematics, which we use that acceleration is 0, what we will get is sigma fx is 0, sigma fy is equal to 0. Using these we will find, so using sigma fx is equal to 0, sigma fy is equal to 0, we find the value of f. The problem is not complete. Then what we do is we also will find the value of n. and then we check if f is less than or equal to mu s n or not. We have the value of f, we have the value of n, we will do this check. Mu s generally would be given to you. So, therefore, you check this. If this is satisfied, assumption is okay and we have found the right solution. But if we find if f turns out to be greater than mu s n, then the no slip assumption is incorrect. The assumption we have made of no slip is incorrect because friction force which we are getting turns out to be greater than mu s n. As soon as it becomes equal to mu s n, the body will start to slip. So, that means now we revisit the problem. Now, acceleration will not be 0. The body will start to slip, except of course, in the case of impending slip when the body is just about to move. So, there, and then what we will do is we will put the value of f. We do not know the value of n till now, but we will put f is equal to mu s n and its direction has to be shown opposite of the relative slip between the body and the contact surface. So, the direction of the friction force has to be opposite and we put f is equal to mu s n. So, now acceleration will become the unknown for which problem will be solved. So, this is how one tackles the problems of friction, where motion is not known a priori. Now, in certain problems, it is specified that surface is smooth or frictionless. If that is so, then it is very obvious that in such cases friction force will be taken to be 0. And so, probably then one of the forces or accelerations will be the unknown for which you will be solving. So, this for this the typical word used is that the contact is smooth, surface is smooth or frictionless would be given to you. Now, this was about the friction side. The other side is we have the acceleration. Force is equal to or sum of forces external on the acting outside the particle, this is equal to m times a. Now, let us have a brief discussion on acceleration. If the particle moves in a straight line, let us say the particle is moving like this. So, then if I choose x along the motion of the particle, then acceleration vector will be equal to a times I or minus a times I, depending on if the particle is moving up or down. So, in this case then we have only one unknown for the acceleration. But in a case like this, if my x and y are chosen, let us say I put it as star, chosen like this, then acceleration in this starred coordinate system will have components both along x and y, and we will have to then find a relation between that, and we know the net acceleration has to be along the plane. So therefore, we can find out a relation between acceleration in x star and y star directions. This is if the particle moves in straight line, and acceleration when particle moves in straight line acceleration is not equal to 0 if velocity is changing in magnitude with time. That means the speed of the particle has to change with time for acceleration not to be 0. If speed of particle is constant when it moves in a straight line, acceleration will be equal to 0. So we can, in fact, we have already written this. We wrote the magnitude of acceleration is equal to dv by dt, where v without a vector sign is the speed. Now, this changes, we have seen this before, when the particle moves in a curved path, or when particle moves on a curved path. In that case, what we find is when the particle is moving along the curved path, acceleration has got two components, and acceleration we can write it as equal to I'll just explain these two unit vectors. Et is the direction which is tangent to the path. And En is a vector which is normal to the path, pointing towards the center of the curved path. And by center we mean, if you assume the motion to be locally in a circle, then it is pointing toward the center of the circle. And let us look at this expression again. We have seen this before when we did kinematics, but let us now understand this because this will have a lot of repercussions. So acceleration has two parts when the particle is not moving on a straight line. There is a part which is equal to the rate of change of speed tangent to the path. This is the same as what you get for motion in a straight line. But now an additional component of acceleration comes in when the particle is moving on a curved path, and that component of acceleration is perpendicular to the tangent to the path. It points toward the center, and this is given as v square upon r, and if you recall, r is what we call as the radius of curvature of the path for a general case. Now, we will look at this in a special case when the particle is moving along a circular path. But before that, what we realize is that even if the speed is constant, then there is a component of acceleration v square upon r which is non-zero. This component did not exist when the particle was moving in a straight line. And we can also see it from this equation in the fact that when the particle moves in a straight line, then the radius of curvature is infinity. So therefore, v square upon r becomes 0. But by virtue of the fact that the particle is moving along a curved path, and if its speed is not 0, which will be there because it is moving, then the acceleration has to have a component normal to the path. And this becomes very important when we apply Newton's law, because sometimes particles may be moving with a constant speed, but there has to be a component of acceleration normal to the path, which means a force has to be there because F is equal to m times a. So a force has to be there acting on the particle which will cause this acceleration to take place. And this force, as we see from Newton's law, has to be an external force when the particle is moving. So, how can it come? It will either come, because this is in the tangential, in the normal direction, this will either come through something which is contacting the particle. For example, if I take a stone, tie it to a string and move the stone, I rotate the string so that the stone moves in a circle, then the tension in the string will provide this force which will cause this acceleration. If it is sometimes it is friction force which will do that, as we will see. So, therefore, this force has to be applied on the particle, it has to come from outside the particle. So, now let us look at the special case of circular motion of bodies, which is a special case of the curved path. When a body moves in a circular path, then the first thing is the radius of curvature r, this is nothing but the radius of the circle at all times. Now, let us take the case of uniform circular motion first. In case of uniform circular motion, if you recall, what we had shown was that, so if there is a circle, a body moving on a circular path at this instant, this is the center. So, what we have is there is a component of because uniform circular motion means speed is constant. So, acceleration of this particle, its acceleration is equal to v square upon r, pointing toward the center. And we realize as the particle moves in the circle, the direction of acceleration keeps on changing. And because the speed is constant, we don't have the tangential component. So, we have an acceleration, and so the component of the acceleration towards the center of the circle is called centripetal acceleration, and this is equal to v square upon r towards the center of the circle. So, now from this is from the kinematics viewpoint. From the dynamics viewpoint, as we discussed, there has to be some force which has to be equal to mass times acceleration, and this force has to be external to the body. Now, if circular motion is not uniform, then acceleration has two components. The first component is, as we have discussed, the centripetal acceleration towards the center, and this we said is equal to v square upon r. And the second component is a tangential component, and this will be equal to the rate of change of speed, and this is tangent to the circle at that instant in the right direction. Now, also what we have seen is that we have defined angular velocity v can be written as omega times r, and this omega we wrote as the angular velocity. So, therefore, now the centripetal acceleration can be written as v square upon r. So, that will be equal to omega square r square upon r. So, this will be equal to omega square r, and the tangential component, this is dv by dt. So, this becomes equal to d by dt of omega times r. R is a constant. So, therefore, this becomes equal to d omega by dt times r, and d omega by dt, what we have written here, this is called the angular acceleration. Rate of change of angular velocity, this is called the angular acceleration. And so, what we have is the tangential component is equal to r times alpha, where alpha is equal to d omega by dt, the angular acceleration. So, we have to take care of this when we have circular motion. Even when the body moves at a constant speed, the acceleration has to be there. Now, let us look at a case of a passenger sitting on the rear seat of a car where the car is turning left, and so we assume that, let us say this is moving, we assume it is moving in a circular arc. So, the car was initially moving straight and then it starts to turn left. So, we assume it is an arc of a circle through which the car is turning. So, now if there is a passenger which is sitting in a car, so we are trying to analyze the situation of the passenger. Since the car is moving in a circle, there is a force, it is moving with a velocity v. So, there is a force mv square upon r acting on the car. Now, suppose if there will be 4 tires on the car, and if the friction on the tires which provides the centripetal acceleration. That means the friction force has to be equal to mv square by upon r, and let us say if there are 4 tires, then the total friction force on the 4 tires will sum up to give this value mv square upon r. Let us now analyze the passenger sitting on the rear seat of the car. So, we draw the free body diagram of the passenger. The car is moving like this. Now, what we find is that there is a normal reaction which is coming out of the plane of the paper. The passenger is sitting down, a normal reaction, this is from the seat of the car. The weight of the passenger is in the direction perpendicular to the paper, and normal reaction and weight, they balance each other. Now, on this particle, what we also find is that there should be a friction force between the seat and the passenger. This friction force is perpendicular to n, and in this case the acceleration, what we find is toward the center, and this has to be provided by the friction force alone. There is a friction force which is acting on the passenger, and that is what causes this acceleration. So, in the free body diagram of the passenger, there will be n and w perpendicular to the plane of the paper, and there is a friction force. These are the 3 external forces acting on the passenger, and this friction force has to be equal to mv square upon r, where m is the mass of the passenger. So, this acceleration which the passenger is going has to be provided by the friction force. And notice here, the passenger is at rest with respect to the car, but we have to write the acceleration of the passenger in terms of an inertial frame of reference, and we are assuming any frame connected to the surface of the earth is inertial. So, with respect to a person on the ground, the passenger is travelling in a circle, and so his acceleration is equal to v square upon r toward the center of the circle. Now, if this friction, if the velocity of the car is high, then what will happen is mv square upon r increases, and this may exceed mu s n, which means then if this exceeds mu s n, then friction force will not be able to stop the relative motion of the body. If mv square upon r is greater than mu s n, in this case n is equal to weight, then the passenger will start to slip, and friction force is acting in this direction. So, therefore, this will be the direction of the relative slip. So, the unbalanced external force acting on the passenger is the force of friction between the seat and the passenger, and this force F is equal to mass times acceleration in the central direction or the radial direction, and this we will write it as mv square upon r. So, friction provides this acceleration to the passenger, and the direction of friction is towards the center of the circle. Now, what we can see is if the velocity is such that mv square upon r is less than mu s n, then we have a situation, we have a case of no slip, because friction is less than mu s n, and in this case we also realize that n is equal to mg. So, the condition for no slip becomes mv square upon r is less than mu s times mg. So, this gives us v square upon rg is less than the coefficient of static friction between the passenger and the seat. For this condition we have no slip, the passenger keeps on sitting. Now, once again realize the full picture. This is the car which is turning, we are looking at the rear seat, the car is at this position, and this is the direction of acceleration of the passenger as seen from the ground frame. Now, suppose if mv square upon r is greater than mu s times mg, which of course we also know was the normal reaction, then what will happen? Then the passenger will start to slip. And what do we mean by slip? So, acceleration of the passenger of the car is like this, and what we will find is the passenger, so this is acceleration of the car which is equal to mv square upon r, which is equal to v square upon r, and we have the acceleration of the passenger with respect to the car. So, the passenger starts to slip, and let AP be the acceleration of the passenger with respect to the car. Now, what we find is we have a friction force, but this is not able to generate the acceleration equal to mv square upon r. So, therefore, the passenger starts to slip. So, if this is the free body diagram, that still stays the same. In addition to this, we have the normal reaction and the weight which cancel each other. But if we look at the kinematics, then in kinematics what we find is that we have an acceleration equal to v square upon r, and this is the acceleration of the passenger with respect to the car. So, the net acceleration of the passenger with respect to ground, this will become equal to v square upon r minus AP in the direction toward the center of the circle. And now when we apply Newton's law, what we will get is friction force is equal to m times v square upon r minus AP, and now this friction force will be equal to mu k times n, which will be equal to mu k times mg. And we can, if other things are known, the acceleration of the passenger with respect to the car can be worked out. The minus sign tells us that the passenger will be thrown outwards, and so this is how we will work out a problem like this. Next, let us now take up some simple examples, and from there we will move to more complex cases. We have seen how to apply Newton's laws, and now in the remaining part of today's class and in the next 1 or 2 classes, we will solve some problems where we will use Newton's second law in a direct fashion with F is equal to ma. And as we have discussed, the more complications in these cases will come, because there may be 1 or 2 bodies connected together, they may be connected with a string, they may be touching each other, and then we will have to analyze each of these bodies separately, and we have to analyze each of the kinematics of each of them to find the acceleration and the relation between the accelerations of the bodies. So, as a very simple first case, what we consider is there is a pulley on which we have a string connecting 2 masses m1 and m2, and the string is on, we can say, is mounted on a pulley, and it is given that the string is light, inextensible, and the contact with the pulley, frictionless contact with pulley. And what we have is there is a mass m2, there is a mass m1. It is given to us that m1 is equal to 5 kgs, m2 is equal to 4 kgs, and we want to find the tension in the string and the magnitude of acceleration A of the blocks of mass m1 or m2. So, this is what we have to find. Now, let us start analyzing this problem. What we find is mass m1 is 5 kgs, m2 is 4 kgs, and this is the string which is, I am showing it as a double this thing, this is going on a pulley. Now, the contact with the pulley is frictionless. So, what we find, since the mass 1 is heavier than mass 2, then we know that this mass 1 will start to move down, mass 2 will start to move up if we leave the system as it is. So, then let us start analyzing the problem and solve this. The other thing what we realize is that because the string is inextensible and in frictionless contact with the pulley, the tension in the string throughout will be constant. The magnitude of tension is constant, its direction changes as we go along the string, at least for the non-straight parts, and the direction will change. So, let us draw the free body diagram of the mass 2. But before that, we realize another thing, because the string is inextensible, the magnitude of acceleration of 1 and 2 will be equal. So, these are the two principles we have in mind, that tension is constant and accelerations of 1 and 2 are equal in magnitude. Of course, the reason why we say is the directions we know, one is moving up, the other is moving down. So, we draw the free body diagram of mass 2. Now, on mass 2 we have its weight which is equal to m2g acting down, and the string pulls this mass with a force T, we call it T. So, this is the free body diagram of mass 2. Now, let us draw, because this will move only vertically. So, we have only one direction, it is a one dimensional motion. Let us say y is upwards here. So, what we have is, when we, this is the free body diagram, and when we apply Newton's law, what we get is T minus m2g is equal to m2 times a, because so here we have implicitly we have written here mass 2 is moving upwards because y is in the upward direction. So, we look at the direction. When we write the left hand side, we only look at the free body diagram, all positive forces with a plus sign, all forces pointing downwards because y is upwards with a negative sign. So, we get T minus m2g is equal to m2a. This is one equation. Now, we realize there are two unknowns T and a here. So, to solve for the second unknown, we go to mass 1. So, then we draw the free body diagram of mass 1. This is m1. Now, once again the string pulls this mass with a tension T, which we have said is the same as what was there in the other part, and its weight which is m1g. Now, for analyzing mass 1, I can choose y going downwards. I need not take y going upwards, because here I know a priori I know that mass is moving down. So, acceleration is downwards. So, I choose y going downwards. In some problems, if you come across problems where you do not know the direction of the motion, then you choose your x and y as a particular direction, assume the acceleration to be positive. If it is in the other direction, you will get your answer with a minus sign. So, now here when we write this, what I get is m1g minus t is equal to m1a. Let us look at the other equation. The other equation was t minus m2g is equal to m2a. This was equation 1, this is equation 2, and now I have two equations and two unknowns. So, I can solve them. Let us add these two equations, and what we get is m1 minus m2 times g is equal to m1 plus m2a. So, therefore, acceleration turns out to be equal to m1 minus m2 upon m1 plus m2 times g, and we can also then work out the value of t, and the value of t turns out to be equal to 2 times m1 m2 upon m1 plus m2 times g. So, we can now small checks, very obvious things, but you should just check these things. The dimensions of acceleration are the same as the dimensions of acceleration due to gravity, and so therefore, the coefficient which comes in front should be dimensionless. And here we see this mass divided by mass, so therefore, this is dimensionless. Tension is a force, so its dimension are mass times acceleration. We have a g here, so the coefficient in front should have dimensions of mass, and we do see that m1 m2 by m1 plus m2. These are very small checks, but these you should keep in mind, and with this you can then work out the problems. Okay. Now, let us take, this was a very straightforward case, but let us now take a second case of a passenger of mass m who stands on an elevator on a weighing scale. That means, let us say this is the compartment of a lift on which there is a weighing scale and a person is standing on the lift. Let the reading taken by the lift be W prime. I am taking it as W prime because when we normally we expect the weighing scale should tell you the weight, which we call as W, but what we will see is, depending on the acceleration of the elevator W prime may or may not be equal to mg, where m is equal to mass of the passenger. So, here let us draw a free body diagram of the person. So, we will analyze these cases for different values of acceleration of the elevator. So, first let us take the case when acceleration A is the acceleration of the elevator as seen from a ground frame, and first we look at the case when A is equal to 0. That means the elevator is at rest. It is something like I am standing on a weighing scale. And then what we find is, if we draw free body diagram of the person, we have his weight acting down, and n, this is the normal reaction from the weighing scale. And this free body diagram stays the same whether the elevator is moving or not moving. And then when we look at the weighing scale, then n is the force being applied by the person, and this n will be equal to W prime, the reading which will be shown by the scale. So, now when acceleration is equal to 0, so the free body diagram in all cases will be n and mg, and I am replacing n by W prime because n is equal to the reading which will be shown. Now, when acceleration is equal to 0, we get W prime is equal to mg. So, the weight which the reading scale shows is my weight, which is correct. Now, if acceleration is upwards, so that means is positive upwards, then what will happen is W prime minus mg will be equal to m times a. The free body diagram stays the same, but now the person is not at rest. Person is at rest with respect to the elevator, but since the elevator is moving up, so this acceleration is acceleration of the elevator. So, what we get is W prime is equal to m times a plus g. So, if the elevator is accelerating upwards, it looks as if the person has got some extra weight. And when we take the other case, when the elevator, so once again we have W prime, we have mg, and if the elevator moves down with acceleration a, so if this is the acceleration, then what we have is mg minus W prime is equal to m times a, and W prime will be equal to mg minus ma, where a, let me just use the subscript d to show that it is downwards. So, now when the elevator is moving down, the same weighing scale shows a reading of mg minus m times ad. So, it shows as if the person has lost weight. So, this one has to keep in mind. Therefore, the same scale shows as if the person's weight has changed. So, now let us consider the case if the elevator's cable breaks down so that the elevator is in a free fall. If the elevator is in a free fall, then the downward component of acceleration AD, this will be equal to g. So, let us look at the case of free fall, and once again as we have emphasized, the free body diagram stays the same. This is W prime, this is mg, and the downward acceleration is g. So, then what we will have is mg minus W prime will be equal to m times g, and therefore, what we will get from here is W prime is equal to 0. So, the weighing scale will give a reading as if the person is weightless. There is no weight for the person if he is falling down freely and on an elevator, on a weighing scale. Now, one thing we realize, while we have talked of the change in weights, these change in weights come with the acceleration in downward or upward direction. If the elevator is moving up or down with a constant speed, then the acceleration will be 0 and the weight read by the scale will still be mg. It is only when the elevator is accelerating up or down that the scale changes its reading. So, in today's class, what we have seen, first we looked at the basic principles as to how to apply Newton's second law to various problems, and then we have looked at some very simple examples. In the next class, we will take up some more examples of application of Newton's laws to problems and maybe some more complex examples. Thank you.